Today, the topic of the analog electronics is the BJT characteristics or bipolar junction transistor. So that is the common collector configuration of the BJT. So in the common collector characteristics of the BJT, fact that the collector is common to both the input and output side of the configuration. So figure A show the common collector NPN configuration, and second figure show the common collector PNP configuration. So in this circuit diagram, or in these two circuit diagrams, the collector is common between the input and output side. So its names is the common collector configuration. In common collector configuration, current amplification factor gamma in common emitter connection, input current is base current and output current is emitter current. So the in common collector configuration, here the input current is the base current and the output current is the emitter current. So the ratio of change in emitter current to the change in base current is known as the current amplification factor gamma. So factor in common collector configuration gamma equal to change in output current or emitter current to change in input current or the change in base current. So gamma equal to change in I divided by change in base current. So this circuit provides same gain as common emitter configuration because change in emitter current approximately change in collector current. So del IE approximate equal to del IC. So what is the relationship between the alpha and beta? So we know that here the gamma equal to del E upon del IB. So alpha equal to, also we know that del IC upon del IE. So we can write this gamma equal to del IE upon del IE minus del IC. And also we know that IE equal to IB plus IC, or we can write this equation in the form of del IE equal to del IB plus del IC, and also find the del IB from this equation equal to del IE minus del IC. So the value of gamma will be divided by I del IE equation of the given gamma equation del I upon del IE minus del IC. This is divided by the del IE. So the equation will be gamma equal to del IE divided by del IE upon del IE upon del IE minus del IC upon del IE. So this will be equal to 1 upon 1 minus alpha, where alpha is the del IC upon del IE. So this is the relation between here gamma and alpha. Next, what is the collector current in common collector configuration? So we can derive the collector current formula, and here the collector current IC equal to alpha IE plus ICBO, where ICBO is the leakage current. So IE equal to IB plus IC. Put the value of this equation of IC. So IE equal to IB plus alpha IE plus ICB, and we can find the value of IE. That will be IB upon 1 minus alpha plus ICBO upon 1 minus alpha. And also the equation of emitter current in the form of beta. So IE equal to beta plus 1 IB plus 1 plus beta ICBO. And we know that the beta also equal to alpha on 1 minus alpha. So the 1 plus beta equal to alpha upon 1 minus alpha plus 1. So equal to 1 upon 1 minus alpha. So this is the relation between alpha and beta, where beta equal to 1 upon 1 minus alpha. There are different comparison of different connection of the BJT. So we take here the difference characteristics, and uh, for example, the what is the input resistance of the common base. So in the common base, the input resistance will be low or in the range of 100 ohm. But in common ammeter, the input resistance will be 750 ohms. That is also low, and the input resistance value for the common collector, it will be very high, or about 750 kilo ohm. Next characteristics is the output resistance. So what is the value of output resistance in the common base? Then it will be very high, about 450 kilo ohm, and the value in common ammeter, this will be 45 kilo ohm, and for the common collector, the output resistance will be low, about 50 ohm. So this is the second characteristics of the BJT. And next one characteristic is the voltage gain. So voltage gain for the common base is 150, and a common ammeter 500, and for the common collector, the voltage gain will be less than unity. And the next characteristics of BJT is the application. So application, common base configuration used as a for high frequency application, and common emitter used as a audio frequency application, and common collector used as a less than for impedance matching. So these are the applications of BJT in different configuration. And next characteristics is the current gain. So what is the current gain for the common base? So it will be less than 1, and for common emitter it will be high, or beta will be high, and for the common collector the current gain will be appreciable. So these are the some comparison of some characteristics for different uh, uh, configuration of the BJT. Now, transistor is an amplifier in CE configuration, or common emitter configuration. So transistor we have as a amplifier in the common emitter configuration. So in this circuit diagram or waveforms between input and output waveforms, figures show the common emitter amplifier for the NPN transistors, and a battery BB is connected. This is the DC voltage supply across the base terminal with base in order to make base forward bias. So this supply voltage make the base to the forward bias, and regardless of input AC polarity, output is taken across load R in this circuit diagram. So the here is the input signal at the input terminal of the this common emitter configuration, and output signal is measure or output measure across the resistance RL. So in this output in case we see here the amplifier, uh, the amplification of the input signal to a low level to high level, or we can say that the output signal is increased with the a particular level of strength. So this is the amplification in this common emitter configuration of the input signals. So during positive half cycle in this input AC, we will keep the emitter base junction more forward biased, so more carrier will be emitted by emitter. This huge current will flow through load, and we will find output amplified signal, that is the output signals. During negative half cycle, input AC will keep the emitter base junction less forward bias, so less carrier will be emitted by emitter, hence collector current decrease in this case. This result in decreased output voltage in opposite direction. So this is the second case in which collector current decrease. Now we discuss about the transistor load line analysis. So what is the load line in BJT? In transistor circuit analysis, it is necessary to determine collector current for various voltage of collector to emitter voltage. One method is we can determine the collector current at any desired BCE voltage from the output characteristics. More conveniently, we can use load line analysis to determine operating point. So, operating point determined by the load line analysis. In this circuit diagram, consider common emitter NPN transistor circuit, and there is no input signals, and apply KCL in the output circuit. So what is the VCE or voltage across the collector to emitter? This will be VCC minus ICRC. And a case first, when the collector current IC equal to 0, then collector emitter voltage is maximum and is equal to VCC. So maximum VCC will be equal to VCC minus ICRC, where IC is the 0, so VCC equal to VCC, and when collector emitter voltage VC is 0, in that case VCE equal to VCC minus ICRC, and put the value of VCE is 0, so IC will be equal to VCC upon RC, that is the maximum collector currents. In this diagram or in this graph, that is draw between IC versus BCE and BCC. So we draw a line that cross the y-axis on the point A and x-axis on the point B. So this line from A point to B point, that is the load line, and at the point of Q, we take a point Q on the load line, that is the operating point, or we can say that is the Q point. So we measure the base current at this operating point Q in this graph. So this will be 5 microampere, very minimum current. And this Q point intersect the x-axis at the point C and y-axis at the point D. So this is the load line analysis, and we can draw the load line of the transistor. Next, what is the operating point? The zero signal value of IC and BCE are known as the operating point. The zero signal value of IC and BCE are known as the operating point. It is called operating point because variation of IC or collector current takes place about this point, and it is also called quiescent point or Q point. So this is the operating point concepts. So the operating point is also called the quiescent point or Q point also. So these are the some fact about the operating point. Now next we will discuss about the DC biasing of the BJT. Biasing means applied the external voltage to the BJT for the operation, that may be in forward biasing and reverse biasing case. And so what is the biasing? So biasing DC voltage applied to a transistor in order to turn on its on so that it can amplify the AC signal. So this is the biasing. Biasing means the DC voltage applied to a transistor in order to turn it on so that it can amplify the AC signal. The DC input establishes an operating or quiescent point called the Q point. So for the establish the operating point, so DC supply or DC biasing is necessary for the establish the operating point. There are the different operating point in this graphs between output current versus output voltage at the different base currents. So the three states of operation, basically active or linear region operation, base emitter junction is forward bias and base collector junction is reverse bias in the linear region operation. And second one is the cutoff region operation, in which base emitter junction is reverse bias. And third one is the saturation operation region, in which base emitter junction is forward bias and base collector junction is reverse bias. So there are three states of operation of the transistor BJT. No matter what type of configuration a transistor used in, the basic relationship between the current are always the same, and the base to emitter voltage is the threshold value if the transistor is in the on state. So voltage base to emitter equal to 0.7 volt, and emitter current IE equal to 1 plus beta IV, or approximate equal to IC. So IC equal to beta IV. So this is the relation between the IC versus IV. The operating point defines where the transistor will operate on its characteristics curve under DC condition. For linear minimum distortion amplification, the DC operating point should not be too close to the maximum power, so voltage or current rating, and should avoid the region of saturation and cutoff. So there are different DC biasing circuits, and there are different DC biasings. So first DC biasing is the fixed bias circuits. Second one is the emitter stabilized bias circuits. Third one is the voltage divider bias circuits. And fourth one and last is the DC bias with voltage feedback. So there are four types DC biasing circuit in this BJT theory. So first we will discuss about the fixed bias. So what is the fixed bias? The fixed configuration is simplest bias of transistor biasing arrangement, but it is also quite unstable. So fixed bias is the also unstable. For most configuration, the DC analysis begins with a determination of the base current. For the DC analysis of a transistor network, all capacitors are replaced by an open circuit equivalent. When we do the DC analysis of a transistor, in that case, all capacitors are replaced by a open circuit equivalent. So this is the example of fixed bias circuit diagram, in which the BCC biasing applied to the base and collector by the base resistance and collector resistance, and DC equivalent circuit of the fixed bias circuit where the capacitor is replaced with an open circuit. So we do the DC analysis of this fixed bias circuit. In that case, we replace the capacitor by the open circuit, and after the open circuit, the circuit equivalent circuit will be like this type of circuit diagram as shown in this figure. So here the capacitors are replaced with an open circuit. So this is the fixed bias circuits biasing. The base emitter loop from the Kirchhoff voltage law. So in the circuit, BCC minus IB RB minus DBE equal to 0. This equation derived by the Kirchhoff voltage law. So solving for base current of this equation, so IB base current equal to BCC minus BBE upon RB. So this is the base current IB, And next one is the collector emitter loop, that is the outside of the circuits. So collector current IC equal to beta IV. From Kirchhoff voltage law, we applied the Kirchhoff voltage law at this outer circuit. So we find that BCE plus IC RC minus BCC equal to 0, and or BCE equal to BCC minus IC RC. So this is the collector to emitter voltage, that is the output voltage, and output current also IC equal to beta IB. For example, determine the following for the fixed bias configuration of the figure shown. So here a figure shown, we can determine the fixed bias configuration. So first is the find out IBQ and ICQ. Second is the BCEQ, and third is the BB and BC, and fourth is the BC. From this circuit or with the help of this circuit, we can find out of these parameters. And here some values of some components given here, just as beta equal to 75 or beta equal to 50, and value of RC and value of RV and value of C1 and value of VCE. So in this example, we also find these values with the help of this circuit and DC analysis, and we can easily find out these values. What is the saturation? Saturation conditions are normally avoided because the base collector junction is no longer reverse bias and the output amplified signal will be. For a transistor operating in the saturation region, the current is a maximum value for the particular design. Change the design and the corresponding saturation level may rise or drop. So the highest saturation level is defined by the maximum collector current as provided by the specification sheets. So there is the saturation position in this graph. That graph drawn between IC versus VC, or output current versus output voltage. So there are some Q points also at the IC saturate current, and some have the value of VCE saturate voltage at the Q point. So these show the saturated value of the IC and VC at the Q point. So in this circuit diagram, we can find the value of RCE equal to BCE upon IC equal to, put the value of BCE 0 and IC saturate. So RCE will be equal to 0 ohm, and also I saturate equal to BCC upon ICC. So this is the also analysis of the DC analysis of this circuit diagram. And in saturation, when the transistor is operating in saturation mode, then current through the transistor is at maximum possible value. So here IC saturate will be BCC upon RC, and also BCE equal to approximate zero voltage in that saturation case. In the previous example, the saturation level for the network is given by IC saturate equal to BCC upon RC and equal to put the value of BCC and RC. So here the value of given BCC equal to 12 volt and value of RC is 2.2 kilo ohm, and we can find that the value of I saturate is the 5.45 milliampere. So these are the in case of saturation, the DC analysis of the BJT. These are the some reference books. Electronics device and circuit, that is by Burma and Halkias. And second book is the electronics fundamental, that is the by Bell. So these are the two books which cover these topics, transistor and its characteristics. There are some multi-choice questions. So these questions are very important and interesting to understand the concept of these topics. In question first, in a BJT or bipolar junction transistor, option A, the base region is sandwiched between emitter and collector. Option B, the collector is sandwiched between base and emitter. Option C, the emitter region is sandwiched between base and collector. Option D, none of these. So here correct answer is A, the base region is sandwiched between emitter and collector. So base is the sandwich between emitter and base. So correct answer here is the A option. Next, a amplifier and oscillators using BJT operates in region. In this question, if we use a BJT as a amplifier or oscillator, in that case, the operation of BJT will be in the option A inverted mode, option B in active mode, option C in cut off mode, and option D is the saturation mode. So correct answer is here option B, which is the active mode, because for the amplification and use as a oscillator of the BJT must be operate in the active region. So here correct answer is the option B, active regions. Next, in a BJT, as a collector to base voltage increase the emitter current. In this question, the question says that in a BJT, collector to base voltage increase the emitter current. Option A remains same, increase slightly. Option C decrease slightly, and option D depend upon doping of the emitter region. So correct answer here is option B, because when we increase the voltage, across the collector and base. Proportionally, the emitter current also increase. So here correct answer is the option B, in which emitter current increase slightly. So here the current of emitter is depend on the voltage across the base and collector in the BJT. So in the next question, the BJT was invented by W.H. Wheaton, Verdine, option C, William Scottley, and option D, all of the above. So here the correct answer is the option D, that is the BJT was invented by the W.H. Breton, also by the Vardin and also William Shockley and all of the above. So correct answer is the here option D. Next, the power rating of a BJT is determined by which of the following. The power rate of the BJT is determined by which of the following. So option A, collector base area, option B, base width, and option C, heat sink, and option D, emitter base junction area. So power rating of the BJT determined by the collector base area, because the area of base be kept the minimum as possible as well possible, and the area of the collector will be large as compared to the base, because in which collector area all charge carriers are collected by the collector's terminal or collector region. So here the correct answer is option A. The power rating of BJT is determined by the collector base area. Now, next, CV transistor has, CV means common base transistor, in which the base is common between input side and output side. So this is the common base transistor configuration. So here option A, in common base transistor, lower input and higher output resistance. Option B, low input and output resistance. Option C, higher input and lower output resistance. And option D, none of these. So here the correct answer is the A for the common base configuration of transistor, where lower input and higher output resistance in the common base transistor. So input resistance will be lower and output resistance will be higher, or in the common base transistor configuration. So correct answer is option A. Next, In a transistor, a highly doped part is highly doped part in a transistor. Emitter, option A emitter, option B base, option C is the collector, option D is the none of the A. So in transistor, there are total three terminals. One is emitter, second terminal is base, and third terminal is collector. So we doping the highly doped part of the transistor is emitter, but in the base we very lightly doped, and the collector region is moderately doped. So in transistor there are total three layers of the semiconductors, in which one layer is emitter or one terminal is emitter, second layer is the base or second terminal is the base, and third one is the layer is collector or third one terminal is the collector. So here emitter is the highly doped with the doping material. So correct answer is A. Next one is in a transistor with normal bias. Option A, the emitter junction offers high resistance. Option B, the emitter junction reverse bias. Option C, the emitter junction has a low resistance. Option D, none of the above. So in this question, a transistor with normal bias. So here correct answer is the emitter junction has a low resistance. So in transistor, in normal biasing case or condition, the emitter junction has a low resistance. So correct answer is option C here. So these are some multi-choice questions. So thank you. Thank you very much. In next lecture, we discuss the remaining parts of this transistor, BJT characteristics, and what is the next. We will discuss about the AC analysis for the different configuration, common base, common collector, and common emitter also. So we will discuss the remaining parts of this topic, BJT. So